actually going to compute the first order condition with respect to investment. So I've rewritten the Lagrangian here, and this is the beast we need to tame. And if I were actually looking at this on a test, of course, this is a huge mess, and it's really easy to get lost in the sauce. So my recommendation, my strong recommendation, what I would do if I were tackling this, is to rewrite the problem, ignoring everything that is not relevant to the derivative we're about to take. So what I'm going to do is I'm just going to rewrite L by scanning through this and just looking for components that have an IT. So for example, I see an IT here, and I'm going to multiply it by minus lambda t. So I'm going to get minus lambda t IT. And then continuing to scan, I have an IT here, so I'm going to get minus qt times minus phi t IT. So we'll get plus qt phi t IT. And then I see an IT. There's an IT inside of this phi t plus 1. We saw that in the last video. So I'm going to have beta. This is going to be a plus because we have a minus sign here and a minus sign here. So it's going to be plus beta times the expectation at time t of qt plus 1 times phi t plus 1 times it plus 1. Okay, and the only downside with this is I need to be very careful to make sure that I did not erase something I need. And I don't think I did. So there's an IT here, there's an IT here, there's an IT plus 1 here, but we don't care about IT plus 1. We only care about IT. And that's all. Okay, so now this is the Lagrangian I'm actually going to work with. And you see that I've reduced it a lot. I've erased a lot of things. And why can I erase these things? Of course, we can't. These terms are all still there. We're just focusing on these ones because we know that everything else will go to 0 when we take the derivative with respect to LT. Okay, so the next thing we need to do is handle these phi t. And what we need to do is pre-compute the derivative of phi t with respect to it. Why should we do this? Just to be a bit cleaner. Again, we could charge in, we could just make the substitution, you could do this all, and if you're comfortable with it, do it. But for me, I would take this in pieces. What was phi t? This was gamma over 2 times it over it minus 1 squared. And so when we take the derivative with respect to it, we first have to take the derivative of the outside. So we'll get minus gamma it over it minus 1 minus 1. And then the derivative of the inside, which we just have this constant it minus 1. Constant from the perspective of it. So it'll look like this. And then for phi t plus 1, because we also have this, still with respect to it. Now we're just going to increase the indices. So we'll have it plus 1 over it minus 1 squared. And the derivative of this, once again, we'll have a minus gamma on the outside. On the inside, do the product rule here. The 2 becomes a 1. Everything on the inside stays. Derivative of the inside, we have constant it plus 1 with respect to it. And then we have to take the derivative of 1 over it. And the derivative of 1 over x is just minus 1 over x squared, right? So we'll get 1 over it squared. And then this minus will become a plus. Let's erase this and erase this. So these are our derivatives. So all of this was just setting up the problem. And again, in principle, you don't have to do any of this, but I strongly recommend it, especially if you're feeling uncomfortable with your speed or you're feeling uncomfortable with these big, messy derivatives. So now let's actually do the problem. Let's take the derivative of L with respect to it and set it equal to 0, which will give us minus lambda t plus qt. And now we have a product rule. So I'm going to start symbolically. I'll just write the derivative of phi t with respect to it. So derive left d right, and then right d left. So we'll just have phi t, and the it derivative of it with respect to it is just 1, right? And then we add to this beta expectation at time t, qt plus 1, phi t plus 1. Let's write it symbolically. Derivative of phi t plus 1 with respect to it, and then times it plus 1. So we're almost done already. Now we just need to plug in the derivatives that we computed. Maybe like this. I'm trying to balance not blocking with my face and seeing the things that I wrote down already. So we have 0 equals minus lambda t plus qt times this derivative we wrote down. It's this one right here. So it's going to be minus gamma it over it minus 1 minus 1. And then we had 1 over it minus 1. We'll write that as it over it minus 1 plus phi itself, which we remember was 1 minus gamma over 2 it over it minus 1 squared, close parenthesis, close bracket. So this is this term. And now we add plus beta times the expectation of the derivative of phi t plus 1. So we have qt plus 1. The derivative of phi t plus 1 we worked out, it's this one right here. So we just have to put it in, gamma it plus 1 over it minus 1, all in parentheses. And then we had it plus 1 over it squared, and we're multiplying that by it plus 1. So we can bring everything into the square. It plus 1 squared over it squared. So there, I put both of the squares on the outside. Close parentheses, and you're done. So this right here, let me scroll the screen up to make sure nothing is blocked. This right here is the derivative of the Lagrangian with respect to it with the penalty term. And as you can see, it's very messy, and there's nothing left really to simplify. Maybe we could just move this lambda t to the left here. Is there a way to do a sanity check on this? There is. And the way to do that would be to cast it into the steady state and see what you get. So what we'll do in the next video, we're going to take this equation, we're going to take the first order conditions we found for capital, next period capital, the first order condition for labor, and the first order condition for consumption. We're going to find the Euler equation. We're going to find the supply curve for labor, and we're going to find the function for Tobin's cube. And then we'll cast it all into the steady state and make sure that we got something that makes sense. So I will see you there.